Hello everybody and welcome back to Advanced Functions. Today we're going to be doing chapter 3.2, which focuses on the reciprocal of a quadratic function. So essentially we'll be following the same steps we did last time. However, since this is talking about quadratic functions, we're adding a little bit more in-depth content to learn more about them. So let's get started. At first, we're going to once again analyze the function just like we did in the previous video. So the reciprocal of a quadratic function has the form as follows. It might look complicated at first until you realize that it's literally a number, divided by the quadratic function that we already know. I just didn't use the values a, b, and c because I used a as our numerator. So again, the form of the function allows us to know very key information such as its domain, range, and its asymptotes. Again, the domain can be found by first of all finding a asymptotes, which is the value of x where the quadratic equals 0. Then you should state that x cannot equal those values. To find the x values, you must first factor the quadratic function. What you have to know is that since we're dealing with quadratics, it will be difficult, or it might even be impossible, to find perfect factors, which I will start to discuss on slide 5. For these first couple of examples, I'll be using a factorable quadratic function. So, if it is factorable, the domain will be x is an element of all real numbers such that x cannot equal the factor you found. When considering the range, you could find it by analyzing the behavior of the function as x approaches the vertical asymptotes from the lefts and rights, and again as x approaches positive and negative infinity. Again, when dealing with different types of functions, you might have to find the local/maximal point to find the restrictions on the range. This might seem a little bit complicated, which is why we will do this following example on the next slide. So let's analyze the function f of x is equals to 1 divided by x squared minus 3x minus 4. So what we first of all can do is rewrite the function as the following. F of x is equals to 1 divided by x plus 1 and x minus 4. So we factored it. Since we found the factors, we can now find the x-intercepts, or in our case, these values would be the vertical asymptotes at x equals to -1 and x equals to 4. What we have to do now is analyze the behavior of the function by substituting values for x from each of the intervals we found. So our intervals would be the values of x that are smaller than -1, so from -1 to infinity, from negative infinity to -1, from -1 to 4, and from 4 to positive infinity. You could do it by first of all analyzing the sign of x. So let's substitute the value of -2 into the equation, right? So we have -2 plus 1, which is a negative, times a negative, that would be a positive. So 1 divided by a positive would be a positive. So this is why we're getting a plus. Now let's do a number from -1 to 4. Let's do 0. So we get 1 times -4, which is a negative. So we get a negative sign of f of x. Lastly, we need to choose a number between 4 and infinity, which would be rather easy, as I would choose the number 5. So what we have would be 5 plus 1, which is a positive, 5 minus 4, which is a positive. So 1 divided by a positive number would mean it's also a positive. So that's how we got those numbers here, or these values here. Okay, now let's discuss the sign of the slope. When it comes to the sign of the slope, we're going to be using the definition that I showed you yesterday, which will be the following. I talked about how when we're analyzing a graph, right, we could have a negative slope or a positive slope. In our case, we have 3 branches, actually, as we have 3 different intervals. For the first branch, it will look something like this. you could, of course, plug in your values and see as they are increasing. Therefore, it is a positive slope, as we have here. Then we have positive to negative. You might be confused about what that would look like, but if we're going through positive to negative, that means these two parts have to be connected, right? So we're having something like this that is then connected to something like this. So you're going to a positive slope and then a negative slope. This makes perfect sense considering the fact that we have two asymptotes. So we have a first asymptote on the left side that looks like this. Then we took this part and put it over here. So we made like an upside down parabola and another branch. That's why we're going to positive and then to negative. The way you would know this is essentially just the format of the graph itself. The more you do these questions, the more you realize they all have the same format, which I will talk about in a couple of slides. But that's the reasoning for these signs of the slope. So the most important thing to take away from this is that we see there's a change in signs between -1 and 4, which would imply there's a maximum point that the branch reaches before it begins to decrease. The way that you come to this conclusion is also rather simple. Just think about a parabola. Like, you're going up, 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 and then at a certain point, right, you're starting to decrease. So it reached a maximum point and then it started going down. So since we have a maximum point and we're still visualizing this or like thinking in your head about a parabola, you could think of it as like the vertex of this branch. So to find the vertex, you might remember you simply could find the average x value, or the x value right in the middle of the 2 points that you have. And the 2 points that we have is actually the vertical asymptotes. The reason for that is even though we can't touch those points, these are still the interval points that we have been given. So the average of the two, or the middle part of them, would be found by adding them up and dividing it by 2. So we get -1 plus 4 divided by 2, which is 3 divided by 2, which is x is equals to 1.5. So we found our x value. Now we have to find our y value. To find our y value, we simply just substitute the found x value into our equation. And what we get is f of x is equals to -0.16. So our vertex is at 1.5, -0.16. Now, as I mentioned before, we have 3 branches, right? And we found that this particular branch has a range of a y being smaller than or equal to -0.16. The reason why it has to be smaller or equal to is because, again, we were going, we have a negative sign, so it is below the x-axis, and then we have a positive to negative, so it reaches negative infinity. That is why it has to be smaller, and then it's equals to, because that's the maximum point it reaches. Lastly, we need to analyze the other 2 branches that we have. We could simply do this by using the method we learned last class, which actually I will show like a mini walkthrough once again on the next question, as I will be showing you how to find the actual asymptotes really efficiently. But overall, what we found is that the range for this function would be that y is greater to 0, or that y is smaller than or equal to -0.16. As you can see, this type of question has 2 restraints. Now, we have to discuss the asymptotes of the function. As you saw in the last example, the vertical asymptotes can be found by factoring the denominator and finding the x value for which that denominator equals to 0. Simple things that we've been doing all along, nothing difficult here, so that's good. To find the horizontal asymptote, it gets a little bit more complicated, but as long as you understand the basic concept, you can literally memorize it and don't have a problem with it after that point. So to find the horizontal asymptote, we could first of all analyze what happens to x as it approaches negative and positive infinity. So let's think of when x approaches negative infinity. We get a really big negative value which I described as a very small value, such as negative 10,000. Okay, so if we substituted negative 10,000 into a quadratic of the form we had before, let's find it. For example, here we have 10,000 to the power of 2. We get a really big number, right? So now what we're doing is we're dividing 1 by a very large number, which would mean that the value overall becomes really, really small. And that would approach 0 as long as we make x big enough or like small enough in this scenario. The same thing happens when we use a really large, small number, a very large value for x, such as 10,000 or 100,000. Again, we're going to be dividing 1 by a very large number, and again, this value will be approaching 0. So what we find is that the horizontal asymptote is once again at y equals 0, just like it was when we were dealing with the reciprocal of a linear function. So since we found that there's a horizontal asymptote of y equals 0, that is the reason for the two branches having a range of y's greater than 0. Because as we looked before, again, we were positive and positive, so we're above it. Henceforth, we have to have y being greater than 0. If we were to put a negative sign, these two values would just be switched. So we have y is smaller than 0, and then y is greater or equal to 0.16. Okay, now let's talk about finding the intercepts. This procedure is the exact same one that we had in a previous class. Simply just find what you need. So if you need to find the x-intercepts that we know we can't have since y cannot equal to 0, just substitute y equals to 0 and you'll know you can't solve it. Then to find your y-intercepts, simply plug in x equals to 0 into the function and solve for y or solve for f of x. However, it is very important to notice that, for example, in some cases, the two vertical asymptotes are symmetrical if they are symmetrical about the y-axis, such as x is equals to plus negative 3. The y-intercept that you find will also be the vertex of the middle branch that we talked about, which actually makes your life a whole lot easier since you don't need to go over the same steps again to find it. Now let's talk about different types of reciprocals of quadratic functions. So far what we have looked at was an example of a reciprocal of a quadratic function that could be factored fully. However, if you recall back to grade 10 or grade 11, there's different types of quadratic functions that we could have. One of them being a quadratic function that has no real roots. For example, x squared plus 1. We're starting at 1 and then we go to positive infinity, so we never cross the x-axis. Hence, we don't have any real roots. With these types of questions, we could still take the reciprocal of it, but since it had no zeros, now we will have no vertical asymptotes. When you analyze these types of functions, it will have an absolute max and still will have a horizontal asymptote at y equals 0. So, for example, we have this function ig over here, which is defined by the following. As you can see, this part is not factorable. If you applied the quadratic formula, you'd see that the whole equation doesn't make any sense. You would get a square root of a negative number, hence we don't have a real root. So what we could do with these types of functions is say that again we have a horizontal asymptote at x equals 0, at y equals 0, but also we know that we should have a vertex somewhere. The problem with this is that we don't really have a restraining value for how to find it yet, right? Because we would have to find the non-real roots of the function and then take the average of them. So you could try doing that, but that doesn't fit with what we learned in class. Hence, I really doubt that you will be asked to do this in your classroom. But, however, if we were to say just move this function over here, and we had something symmetrical about the y-axis, that makes our life so much easier, because now we could simply find the vertex by finding the y-intercept. So we just substitute x equals to 0 into the equation, and we find the vertex, and we're done describing the graph. There's another type of reciprocals of a quadratic function that you might remember. Again, thinking back to other quadratic functions, you might recall quadratic functions simply like x squared, where it has only one root, but it has the root being of order 2, like we learned in chapter 1. So for these types of functions, we will have only one vertical asymptote. That makes perfect sense as we only had one real root. So now, what we need to do is learn how to describe it or analyze it. This type of question is personally my favorite. It is extremely simple. It looks like a little cone that just reaches positive or negative infinity depending on the sign of the function. So here I graphed the function 1 divided by x minus 9 to the power of 2. What you could see from it is that 9 has to be the vertical asymptote, and we still have a horizontal asymptote at y equals 0. These types of functions just personally make me super happy. They're super simple, as we see here, where we're going from when x approaches negative infinity, we get a very large negative number squared, which makes it a positive number. And then a 1 divided by a very large positive number would give us positive numbers approaching 0, which is why we have a function or a branch that looks like this. The same thing happens on the other side. That's why these just personally make me super happy. Again, we have a quadratic function that has 2 real roots, which is the exact same questions we discussed in like slide 3, if you remember that. Those are probably the ones you're going to be tested on the most, just because they require a lot more steps to be solved. But again, they're nothing too worrisome. If you just pay attention to the intervals that you have looked at, you shouldn't have any problems. So for today's homework, I don't think I changed the page. That kind of is unfortunate. We have these questions. There's quite a lot of them, just because again we're dealing with 3 different types of quadratic functions. But they all follow the same principles, which I will go over once I do them. I will show you the strategies for solving them, and then you could go on your merry way and solving them by yourself. So let's do that now. Okay, so let's look at question 2. I assigned 4 parts here because honestly this question is rather simple. Determine equations for the vertical asymptotes if they exist for each function, then state the domain. So for A, C, E, and G, any type of quadratic function, to find the vertical asymptote, we need to simply find the value of x, which makes the denominator equal to 0. So in question A, we have the denominator being equal to x minus 4 to the power of 2. So we just equate that to 0, and we get that x minus 4 is equals to 0, so x equals to 4. That is our vertical asymptote. Since we found the vertical asymptote, we can now state the domain, which would exclude the value at which the vertical asymptote occurs at. So our domain would be x as an element of all real numbers such that x does not equal to 4. For part C, we have x squared plus 1 equals to 0. So what we get is x squared is equals to negative 1. If we try to take the square root of negative 1, we wouldn't get a real number. Hence, there's no vertical asymptotes for this question. If there's no vertical asymptote, that means x is defined for every number. Therefore, the domain of this function is x is an element of all real numbers. For question E, we have our denominator being equal to x squared minus 4 plus 3. You might notice right away that x squared minus 4 plus 3 is factorable. It is the product of x minus 1 and x minus 3. Since x minus 1 and x minus 3 are the two factors, the value that x cannot equal to is 3 and 1. Therefore, the domain is x is an amount of all real numbers such that x is not equal to 1 and x is not equal to 3. And the vertical asymptotes are x equals to 3 and x equals to 1. Now, we have g, which is n of x is equals to negative 2 over 3x squared plus 2x minus 8. So what we have to do here is factor this equation. So we have to find two values that multiply to 24 and add up to 12, and add up to 2. So a negative 24 and 2. So those values could be, the values would be positive 6x and then negative 4x. Then I personally like to just group them together and then continue to simplify. Once you do that, you will find your two factors, which equal to x plus 2 and 3x minus 4. Since we found our factors, we can now find the asymptotes by making them equal to 0. So our asymptotes would be at x equals to negative 2 and at x is equal to 4 over 3. With our asymptote being found, we can now state the domain. The domain would be x is an element of all real numbers such that x cannot equal to negative 2 and x cannot equal to 4 over 3. Now let's look at question 3. Make a summary table with the heading shown for each graph. So we have to state the interval, the sign of the function, the slope of the sign of the slope, and the change in slope. This is the exact same thing I showed to you during my presentation. However, the difference here is that we have to include the change in the slope. So the change in the slope would be whether or not it is increasing or decreasing. So again, by looking at the chart or the example I showed you in 3.1, you could easily figure that out. So let's solve A, and then you could do part B by yourself. So the intervals that we have here is to the left of the vertical asymptote and to the right. So to the left we would have x is smaller than 1, and to the right it's x is greater than 1. The sign of the function is whether or not it is above the x-axis or below the x-axis. As we could see here, everything's above the x-axis, therefore it has to be positive. The slope can be found by whether or not the function is increasing, like is the values increasing or are they decreasing. So we were going from over here we were going from small numbers to very large numbers. So it is increasing, which I would say is positive. Then over here we were going from very large numbers to small numbers, which would make a downward arrow, which would be negative. Lastly, we have the change in slope. So again, let's imagine what's happening to the graph as it is approaching the vertical asymptote. So as it is approaching the vertical asymptote from here, we see that the values are increasing. And as we look from the other branch, the values are once again increasing. So yes, the change in slope would also have to be positive as the numbers increase as we approach the vertical asymptote. I was looking into my answer book and they had the wrong answer there, so that could happen too. Make sure you talk to your teacher about it so they could explain it to you whether or not you solved it right or wrong. But I'm pretty sure I got the right answer. So part B would be the exact same thing. You just look at the intervals bounded by the numbers they stated here. Then the sign of the Function would be whether or not it is above or below the x-axis. The sign of the slope would refer to whether or not the function is positive or negative, and the change in the slope would be whether or not it is decreasing or increasing. Again, use the same chart or memorize the chart that I showed you last time. So now for question 4. Determine a possible equation for each function in question 3. So since I assigned A and B, I'd expect you to do A and B as well. So a possible equation for function 3a would be that we have a vertical asymptote at x is equals to 1. So what our denominator has to be is a single value of order 2. So our denominator would be x minus 1 to the power of 2. Now we have a y-intercept at 0 and 1. So substitute those values in. So we have 1 is equal to a, which is the top value, divided by 0 minus 1. So minus 1 squared. So what we get is 1 is equals to a divided by 1. So a is equals to 1. Therefore, our function is f of x is equals to 1 over x minus 1 squared. So now for part B. We're given the vertical asymptotes, as you can see here, at -2 and at 4. Therefore, our denominator would be a value of, let's say, x plus 2, x minus 4, right? Then what I'd like to do is again plug in the point we're given here. The top value I would always say is a constant or an unknown, like let's say again a. So what we get is 1 is equals to a divided by x plus 2, x minus 4. So now we substitute in the values and we solve for a. Again, if you do it correctly, you should find that a is equals to 1. Therefore, our function is that f of x is equals to 1 over x plus 2, x minus 4. Now, let's move on to question 5. Sorry. For each function, get the domain, determine the equations of the asymptotes, determine the y-intercept, sketch the graph of the function, include a summary of the table of slopes, and give the range. So what you will be doing is the exact example I gave to you during the presentation just now with all the different types of functions I've introduced to you. So for the first one, personally, I think you should always find the asymptotes first because they're the restrictions for the x-axis. So the asymptote for a would be that x cannot equal to plus minus 3. If you're wondering where I got that from, that's because we're just applying the difference of squares formula. For part C, we need to factor it, so we get a number that multiplies to 21 and adds up to 5. So that would be positive, let's see, 21 and 5. 21 could be achieved by 7, 3. Which doesn't seem to be the case, so perhaps maybe it can't be factored. You could use the quadratic formula to check that one out. Yeah, it seems as though you have to use the quadratic formula for this one, which should be a lot of fun. Then with that, you would say that your x values can't equal to the values you'd found. For E, it's quite obvious that we can't have a vertical asymptote here, so our domain would be x is an element of all real numbers. To determine the y-intercept, just simply make x equal to 0 for all of the equations. To sketch a graph of the function, what you should do is use all the information you found out in the previous 3 parts. So graph your asymptotes first by making dotted lines and labeling them. Then since you have, for example, C is negative, So you would reflect the usual version that you have of the graph in your head. So usually it's this, right? But now it's like this. So this was like a sad face. Now we have an upside down sad face. This person, I like to think about it. And then you again put in the points you found for the y-intercept. It's rather simple. Then it's asking you to include a summary table of the slopes, which is the thing we did in question 3. And finally, give the range. To find the range, again, you should find the vertex. For example, here, we know that it has to be greater than 0, just because of the form of the function that was given to us. For C, we need to find the vertex, which will be a lot of fun to do, since we will have the complicated roots. You'd have to find the average of those two roots and then substitute that into the function to find your y value, and your y value isn't going to be pretty either. As far as I recall, I didn't have any those sort of questions on my tests and examinations, just because they take a lot of time and don't really test the content as well as they do otherwise. So because they just take a lot of time, so don't worry about it. Just try your best, but if time limits you, I really doubt they'll put it on examination. Now let's look at question 6. For each function, approximate the instantaneous rate of change of the y-intercept. Ooh, you might not remember what this is about, but this was from chapter 1 when we learned about AROC and IROC. And if you remember how to do that, what we're simply doing is finding a value that is approaching 0 from the x-intercept, right? Because that's what we're talking about. From the y-intercept. And then you're finding the y value. So then you're going to be comparing the slopes. So for example, for A, we had a y-intercept is equals to 1/9, right? So what you're doing is that you will be writing it out as though the difference of the, sorry, this is a little bit difficult to explain just in words. So you'll be substituting, for example, 0.1 into the equation, then 0.01, then a number very, very close to 0, right? And then you would find your y values and find the differences of those. And what you would notice is that the slope would approach a certain number. That slope, or that difference, is the slope. And that is the instantaneous rate of change that you're trying to find. Because remember, instantaneous rate of change is just your delta y over delta x. For question 8, it's asking you to sketch each function and determine the intervals for where the function is increasing and where it is decreasing. Again, follow the same procedures we have learned. Factor it, find the vertical asymptotes, find the vertex for some of the questions, graph it. Then, since we're talking about whether the function is increasing or decreasing, just look at the behavior the function has when it approaches each of the vertical asymptotes. Then we have question 9, which I thought was rather interesting. Describe how to find the vertex of a parabola defined by the following function. Okay, so we have something that can't be factored, right? Because we're trying to find something that multiplies to 11 and adds to 6. 11 is not factorable, so we don't have any luck here. What you would do is apply the quadratic formula, right? And once you apply the quadratic formula, you could find it, or what you could do is you could try to complete the square, if you remember how to do that. Once you complete the square, what you would do is you would find the vertex. Right? So how would we complete the square here? So we have x squared plus 6x plus 11. So we have something that is x squared plus 6 plus something, which has to make a perfect square. That something would have to be plus 9, right? Because we would have x plus 3 as our perfect square. So if we're plus 3, then plus 9, then we have to subtract 9. So our full new function would be x plus 3 squared plus 11 minus 9, which is plus 2. Therefore, we found the vertex being equal to -3 and 2. Since we now know what the vertex is at, we could now use the method we just found to find the maximum point of the function for g of x. So we found that the vertex is at -3. Therefore, now it is also the vertex of our new function. Now we're just simply substituting in -3 into our new equation and finding our new y value, which is now 1/2. Now this question is just requiring you to apply what you just learned or what you just remembered. So here you just have to complete the square, find the x value, substitute the x value into the full equation, and then find h of x. So it's again rather simple, but it's a very fun and easier way than to simply find the average like I showed you before. Now we have question 11. Each function described below is a reciprocal of a quadratic function. Write an equation to represent each function. So the horizontal asymptote is at y equals 0. Okay, that's for all of them. That's good. The vertical asymptotes are x equals 2 and x minus 3. So we know the denominator would have to have x minus 2 and x plus 3 as its factors. Then for the intervals, x is smaller than -3 and x is greater than 2, y is greater than 0, which means that it is above the x-axis. So if it's above the x-axis and we found our denominator, we could just state that f of x is equals to 1 over x minus 2 x plus 3. The reason why it's that simple is because it's not giving us a certain point it has to pass through, which makes our life a whole lot easier. Now for question B, again it says there's a horizontal asymptote of y equals 0. There's no vertical asymptote. The maximum point is at 0 and 0.5, and the domain is every real number. What we could do here is, since we have a maximum point of 0.05 and we don't have a vertical asymptote, that means we only have one type of function that we can deal with, and that is a function where the denominator cannot be factored. If the denominator can't be factored, that would mean we would have x to the power of something plus something. Now with that in mind, we could substitute our maximum point in. So we have 0.5 is equals to 1 over x squared plus something, where x squared is actually equals to 0. So y is equals to 1 divided by a value. Now simply solving that, you would find that that value is equals to 2. So what we get is that y is equals to 1 over x squared plus 2. Lastly, we have part C. We have a single vertical asymptote at x equals to -3. We have the exact same horizontal asymptote as we always had. And lastly, the domain is x is an element of all real numbers such that x doesn't equal to -3. Again, this is super simple. The only type of equation that would fit into this is that the quadratic would have to have the form of x plus something to the power of 2, since we have exactly one real root. So what we know is that we don't have a given point that we can substitute in. It doesn't tell us whether or not it's above the x-axis or below the x-axis. So I'd simply go with the version where it says y is equals to 1 over x plus 3. The reason why it's x plus 3 because if x doesn't equal to -3, that means that x plus 3 must be the factor. I think that was the last question I've assigned for today. So hopefully you have enough time to finish all the other ones that I didn't explicitly describe. That was definitely a word, I promise you. Now that we're back here at the homework page, I hope you have already forgotten the fact that I couldn't say explicitly, but if you didn't, I hope you had a good laugh. Tomorrow or in a couple of days, I'll be showing you chapter 3.3, which is the last type of rational function we will be dealing with. Chapter 3.4 and 3.5, as far as I recall, are more inequality questions. With that being the case, I hope you learned a lot today. This chapter was a little bit tedious and has a lot of content. However, after this chapter, we're going to be moving into trig. So hopefully you'll have a lot of fun with that. After the news that I heard about the TDSB being back in like a hybrid classroom setting with online classes every day, I felt like this should help a lot of students with mathematics, considering the fact you'll still be learning online, so why not actually use a good online tutorial. Yeah, again, if you have any questions about anything we discussed here or in the previous episodes, be happy to like leave a comment or message me on Instagram or email me. I'll be happy to help you out. Anyway, I hope you have learned a lot and thank you for listening.